Okay.
You are good to go, I think.
Okay. Thanks for the invitation from Rebecca. I'm very happy to be here sharing our work today. So I'm Fan Yao from University of Virginia, and currently I'm a visiting student at the University of Chicago as well, since my advisor moved to University of Chicago. Today I'm going to talk about content creation competition as a emerging phenomenon in content recommendation platforms and the related incentive design problem for the new recommendation algorithms. If you have any thoughts or questions during my presentation, please feel free to chime in. Okay. Uh, so I'll start with an overview of this presentation. I'll first introduce our framework, game theoretical framework for modeling strategic content creation in online recommender platforms. And I'll first present a diagnostic result regarding how the vanilla relevance-based recommendation policy will behave in such an environment. From our paper, How Bad is Top K Recommendation? And then I introduce prescriptive solutions to this observation from another paper, Rethinking Incentives in Recommender Systems. And if we still got time, I can briefly introduce our ongoing work built on top of this, like how the platform optimize the user welfare under the environment created by competing content creators. Okay, so let's start with our motivation. Oh, oops. Okay, so our research is motivated by the remarkable expansion of the content creation economy in recent years. So the market size of the content creation industry is now over 600 billion and is estimated to have an annual growth rate over 16% in the next 5 years. So the booming of this emergent market makes major content recommendation platforms to recognize the crucial role that content creators play in the whole ecosystem. And those platforms have begun to actively support creators to monetize directly. For example, TikTok initiated the Creator Fund program like years ago to allow content creators to monitor how their created content makes money and what their performance are and how they can keep improving the performance of their created content. And similarly, YouTube had initiated the partner program for similar purpose, and Meta Reels had this ads program, like how they can share the revenue gain from ads to their content creators. All these rules are carefully designed by the platform in order to boost the overall quality and the diversity of the whole content ecosystem. So these are evidence that here are some evidence that content creators on those platforms are actually strategically responding to the platform strategies. For example, YouTube engineers and researchers in YouTube have observed that when they use different like metric to evaluate the video's quality and use it as a feedback, creators should have different response. For example, when they use view duration to evaluate the quality, creators tend to make longer videos. And interestingly, if they change their metric to something like the completion rate, then creators tend to make shorter videos because simply it's better for to improving the metric. And in Instagram, we also have some similar observations. When Instagram posts some minimum requirement to enter the monetization program, like the ad sharing program, creators are observed to create some fake followers and the traffics in order to fulfill this minimum requirement. Yeah. So these are all the evidence that the strategic behavior of content creators actually poses some additional challenge for the platform designers. So the challenge can be formalized in this paradigm. So previously, the research for the information retrieval and recommender system mainly focus on designing the mm, most efficient matching function between a static pool of content and a fixed pool of users. However, the content pool nowadays is generated by strategic content creators who aim at maximizing the rewards provided by the platform. So this will lead to a competing dynamic among creators and also causes a shift over content distribution. So a natural problem arises in this picture is that uh, the recommender platform should not only focus on designing the perfect matching function, but to control the content supply is also an obligation of the platform. And our research question here is how can the recommender system optimize the user experience in such an environment? Okay, so here is our model overview. We call it competing content creation game. So we formulate this problem as a repeated game played by content creators. And the user population is assumed to be fixed. And on the content creator side, we assign each of them an action set SI. So each different content creator I could have a different action set SI. At the beginning of each time, each content creator can choose to generate a content within her action set SI, and the joint strategy forms the current content pool, which is a collection of all the SI from N creators. And after observing this content pool S, the recommender system will use a matching function like sigma to evaluate the relevance score between each content SI and the user profile X. And whenever an X shows up, it matches this X with the top K ranked score content to this user. And we should note here the sigma here is assumed to be learned offline. So we're not interested in how we compute this sigma function. Actually, a whole literature of recommender system research mainly focused on how we can efficiently evaluate this sigma. You can use very complex like deep learning model to learn sigma, but this is not our focus of this work. We assume sigma is learned, and we are trying to understand how the arguably simplest recommendation principle, like using the top K relevance metric to assign this matching would affect the user welfare under this strategic environment. And after observing this recommended slot of length K, this user will make a preference choice according to some behavior model. And the recommended system observe the user's feedback and update and reward creators based on the performance. And then the creators will receive the feedback from the platform and update their strategies according to certain learning principles. So this is the whole overview of the game theoretical framework of this model. So to further specify the model, we need to make some detailed explanations. So on the creator side, we need to make some behavior assumptions. So this is a mild assumption we make here. We assume that each creator can observe a utility function, which is given by the specific policy, rewarding policy of the platform. So here the UI SI means when the creator I choose to create content SI, what is the expected utility you can get from the platform? And of course, this utility would also depend on other player strategies, which we denoted by S negative I. So here S negative I means all the other creator strategies except SI. So UI is a joint, is determined by both SI and other strategy S negative I. And no regret learning principle is a commonly used like a principle in the online learning literature. It basically means that if I am creator I can propose any strategy to generate the creation sequence during the time horizon t, but at the end of time horizon t, I compare this sequential the utility, like cumulative utility I get sequentially compared to the best fixed action in hindsight. And I find out I would not regret not using any fixed strategy. Yeah. So many various efficient learning algorithms can realize this goal in our setting. For example, the ESP3, like the whole family of mirror descent and FTRL algorithm. Yeah. Well, we're not saying that the creators should strictly follow this algorithm. These are just some examples that can indeed achieve this no regret learning behavior. And on the user side, we employ the famous random utility model in the econometric literature to explain the user's behavior in general. So let's suppose a user is presented with three relevant recommendations with different scores, and we'll say the user's perceived utility in her eyes is the true relevant score plus some noise. And the user's choice is like the argmax among these perturbed relevant scores. And if we assume this noise follows Gumbel noise, and then the user is expected the utility is exactly given by the choice function is exactly given by the softmax distribution, and we can define the user's expected utility accordingly. And the total user welfare is thus defined as the total expected utility that can be collected from all from the user population. And this is the target that we aim at analyzing. And finally, we need to define what is the creator's utility. And that depends on the platform's specific rewarding mechanism. So here we consider the popular choice from the platform, which is the engagement-based metric. So remember, S is the joint strategy profile across all the creators on the platform. And the share that the creator I will get from the platform is proportional to the user engagement it will get in expectation. So for each user X, the expected engagement of this creator I is proportional to the relevance score plus the noise and dot the probability that the X is actually X will indeed visit this creator I's content. And remember that this probability is given by the softmax distribution, but this is not important here, so we just show it in the abstract form. Now, if it's an online video sharing platform, you can view this metric like something similar to the expected watch time. Yeah, and the social welfare under this engagement metric actually has a very nice property that is the user side welfare and the creator side welfare are actually aligned in the sense that if we sum up all the creators utility, it also equals to the sum of the expected users perceived utility. So that's why this engagement metric will have some good property like we will show later. This is because the platform deliberately align the reward metric on both sides. And then we try to analyze how this top K recommendation policy would behave in such environment. So our first theoretical result states that if in our game C3, if all content creators use no regret learning algorithm, and what eventually the social welfare metric WS would be. No, the metric we will use here is the notion of price of anarchy, which is a very acknowledged notion in game theory literature. It measures the intrinsic property of the game, which is defined as the maximum possible welfare that can be achieved among all potential strategy profiles, uh, divided by the actual realized social welfare from the game, then the dynamics induced by the game structure. So in our case, the denominator is the actual accumulated total welfare induced by all the players' no regret learning strategy. Yeah, and if we take the expectation over the whole time horizon T, this is the actual average user engagement the platform will receive during a fixed time horizon T. And we can see that the POA of the game G, if this value is very large, then it means the result is not good, because it means if the platform can dictate what each content creator will produce, it will receive a much higher potentially social welfare. But however, if we simply allow content creators to evolve on their own, they are all being selfish, they're trying to maximize their own utility, then the resulting welfare will be very small. This is what it means when the price of anarchy is a very large number. So large is not good, and a smaller number approaching 1 is a good result. Okay, so our result says that the price of anarchy of this game can be upper bounded by 1 plus a constant, depending on two crucial factors, beta and k. So because we are already assuming creators are using no regret learning strategy, so you can see the term RT over T will shrink to 0 as T goes to infinity. So the second term on the right-hand side is essentially depending on the factor 1 over C beta K. And C beta K is a very complicated function, but approximately it equals to 1 plus beta times log K, where beta is the user decision noise, the level of user decision noise in the Gumbel distribution, and K is the length of the recommendation slot. So what does it mean? So if the beta is very large, meaning the users on the platform in average is very like explorative, they're willing to explore different possibilities. They're not very restrictive to their own preference. Then overall, the user welfare under against the selfish behavior of content creators will be very good. And also, if we increase the recommendation slots, meaning the recommendation platform provides more choices to each individual, the user welfare at the end will also be very good. So this and so to summarize, our upper bound result can be summarized in this form. So what we can see is that when k is a reasonably large number, then we can conclude that uh, even under the top k, the simplest top k recommendation policy, and the system platform does not introduce any possible intervention, the efficiency loss in terms of the user welfare is less than half. And a larger recommendation slots, like increasing K or increasing beta, will lead to a better user welfare. And we also show that this bound is tight. Yeah, we will not go through the proof details of this theorem. We just get the sense that this is the intrinsic property of the top K recommendation. So this is an interesting result in terms that it equals like the Adam Smith's argument It's like there is an invisible hand in the online content matching industry that the platform can simply there's no intervention and simply let each content creators to selfishly choose what content they want to create, and eventually the we see and the market is efficient up to a constant level. But this positive result hinges on two crucial assumptions. The first one is that the creators can indeed follow no regret learning principle, and the platform need to provide aligned incentives between users and the content creators. Yeah, and in the remaining of our talk, we'll see what if these two assumptions are not exactly satisfied. And so we will first see what if the platform does not provide aligned incentives. For example, hello, I see Rebecca raised her hand.
Sorry, before you continue, I just have a question. I'm having trouble like concretely visualizing what it means to have no regret learning in terms of a content creator, right? Because what you're saying here is that uh, a content creator has to continue to create at
Oh,
the maximum of their engagement. So, like if they have a YouTube, let's say you're a YouTube creator, and yeah,
I see.
is that correct? Mhm.
Right, right. So no regret learning assumption is indeed a very mild one. I can give you another example. Each creator can, if each creator can exactly observe the form of her utility function UI, then simply using gradient descent, like projected gradient descent to optimize this function is already a no regret learning principle. Yeah,
Yeah. No, I understood it mathematically. I guess I'm
Oh,
thinking in
okay.
terms of, right,
Oh,
since
oh, okay.
content creation is not engaged with through gradient descent. It's something that someone has to continue to do. So they have to, so I guess I'm thinking like, is how would this translate into the reality of content
Oh, I
creation?
see. I see. In reality, you can imagine this as we require each content creator to actively monitoring the behavior of the created content in each round, and trying to make an improvement given all the information she might have. Uh, yeah, that's probably the high level principle we need to impose on each creator. Yeah.
So then, just to make sure I understood, is it continuous improvement, like greater than for the utility to be continuously increasing, or can it be greater or
Not
equal?
necessarily. It could involve some randomness. Yeah. For
Hmm.
example, another example is that the content creator is not able to evaluate the gradient, which is very typical, right? They only have access to the point estimation of this UI. Yeah, this is what is really happening in reality. But if they can keep in every time they can propose a random direction to improve their utility. Yeah, and then decide whether it is acceptable or not. Yeah, this is essentially corresponding to the zeroth order optimization in the optimization literature, and this is also a no regret learning principle. Yeah,
Okay,
so yeah,
got
you
it.
can
Thank
indeed
you.
see, yeah, this is very mild assumption. Okay. Okay, so what if the platform does not employ this so-called engagement-based metric? So another popular choice is like simply rewarding each content creator proportional to the traffic they will get. So we simply remove the part that is proportional to the user satisfaction part. And the new metric is simply saying each creator will be rewarded proportional to the traffic. And the results is suddenly the user welfare guarantee will drop significantly in the sense that the price of anarchy, which is the reciprocal of the left-hand side, can be strictly larger than 2. Here is an example showing why this simply traffic-based like metric is just not as good as the engagement-based one. So you can see there are three cluster of users. And the left figure shows that if creators is simply rewarded based on the traffic they will get, the one possible equilibrium outcome of this game could be that all the creator will agglomerate around the geometric center of these three different user clusters. Each of the creator will not have this additional incentive to further optimize the relevance between her content and each user group. But this is because even though they don't optimize the relevance score, they can still get a very large share of the whole population. In this example, each creator will still get 1/3 of the whole user traffic. But you can see the user engagement defined based on the relevance score will be very small. But if in our previous result, yeah, well, when creators are rewarded by engagement, we make sure that each creator has the additional incentive to further like improve their relevance between their content and the user cluster, so we achieve a better social welfare. So here is an diagnostic result, what is the performance of the top K recommendation principle in this environment. And in reality, theoretically, we can conclude that this is not so bad because 1 over log K is a very small factor. But in reality, this K cannot be very large. It's usually at the order of 10 or so. So there is still a significant loss in terms of the user engagement. So our next question is, if the platform can indeed design some more sophisticated incentivizing plan for the content creators, is there additional room for the improvement in terms of the user welfare? And the answer is yes. So this is what our next paper is trying to focus on. So we're still in this same framework. So the recommender system learns this matching function sigma, and what's the additional part is like the platform will no longer reward the creators based on either engagement or like the traffic-based metric, but instead it will employ a very general metric. Like he will use a function m to decide what creator I will eventually get for this created content si. So you can see that the function m takes input of sigma I, which is the relevance score between creator i's created content and other, and the sigma negative I is the vector of the relevance score from all the other creators' strategies. And the form of the function m will decide what is the monetary reward you will get from the platform. So we will also generalize the user behavior model in our previous framework because previously we only allow each user to pick the most relevant content to consume. And now we introduce this the position bias in the ranking result, and to define the user's expected welfare from a session as the weighted sum of the relevance score on different ranking positions. Here you can see RK is given by, for example, given by the NDCG principle, and so we actually allow each particular user to consume the different number of items in a recommendation slot. And we also generalize the social welfare definition by incorporating the utility from 3 parties. So previously, our social welfare only concerns the user utility, right? But now social welfare is defined as the user welfare plus the creator's utility and minus the platform's cost. Because now we're in a a different setting. The platform is no longer rewarding them based on some simple traffic or engagement metrics. They're actually rewarding them with money, with real money. Yeah. So our first theoretical result says that um, for very broad class of such rewarding mechanism M, as long as they satisfy two basic principles, it will never be able to optimize the user welfare because they will always introduce a 1 over k fraction of social welfare loss at the equilibrium of this game. So, so what does this, so this equals our previous result. Remember that if the platform use the engagement metric, the price of anarchy can be lower bounded by 1 plus 1 over log k. But now we're saying that this result can be generalized in the sense that for even broader class of rewarding mechanisms, the price of anarchy is still lower bounded away from zero with a smaller factor 1 over k. But it still shows that the welfare optimization is why the welfare optimization is hard. Okay, so let's explain in what sense we generalize the previous results. So what does this individual monotone and group monotone mean? So individual monotone says it's a very straightforward principle. It says that for any user X and any creator I, if the creator I changes her strategy to increase the relevant score between Si and X, then the platform should always reward this creator with a higher reward. Yeah, this is obvious and straightforward, right? And no platform wants to violate this principle. And the group monotone means that still for this user X, and we consider a group of content creators who have chance to be exposed to this user X. If one of them increased the matching score, then this group of creators collectively would receive a higher reward in total. Yeah, this principle is not as straightforward as the previous one. But what we observe is that currently the many popular rewarding mechanisms falls into also satisfy the second principle. For example, you can imagine a vanilla rewarding mechanism, meaning we don't care about what other creators behave. We simply look at the performance of your content, and the reward is simply proportional to the relevant score of your created content to this specific user X. Yeah, and the two rewarding principle like exposure-based and engagement-based metric also satisfy this group monotone. Yeah, we can easily verify this fact. And our impossibility theorem says that any rewarding mechanism satisfies these two abstract principles will necessarily suffer a 1 over k fraction of social welfare loss in such under the competing content creator environment. So that means if we want to optimize the social welfare, at least one of them we need to get rid of, right? Since the first one is a straightforward one, we need to get rid of the second one. Yeah, that means we need this rewarding principle to reflect the competition nature among content creators. So if one content creator increase her relevant score, but it's not necessarily that I need to reward this whole group of content creators as a whole. Because it could be that this area is already very crowded. The platform doesn't want any additional creators to jump in this field. So if you keep increasing your relevance score, keep putting additional effort in this area, the flat platform would not reward you anymore, but instead the platform might want to punish you because the platform want you to diverge, you diverge your attention to some other niche field. Yeah, this is why we want to get rid of the group monotone principle. So this is the solution we propose. Yeah, it's very abstract, but we're trying to explain it in this figure. So let's suppose the platform wants to decide how much reward I should give three creators for a particular user for producing three pieces of content with relevance score sigma 1, sigma 2, and sigma 3. So what the platform will do is to design three functions, F1, F2, and F3. And first, the platform will decide what is the reward for the lowest ranked content creator. And this reward should be proportional to the area under the curve of F3 from 0 to sigma 3. This is a reward for the third ranked creator. And for the second ranked creator, the reward should be higher than the third one. And the additional part is exactly assigned to be the integral of the function f2 in the interval from sigma 3 to sigma 2. Yeah, and this principle goes on until the platform assigns the reward for the highest ranked creator. So this is how the platform will create reward each content creator based on the realized observation of the relevant score. So we can easily see that such a rewarding mechanism is compatible with the top K recommendation principle. Because if this platform simply wants to reward the top K ranked creators, you can simply set the function from fk plus 1 to fn to be 0. And this naturally satisfies the individual monotone. As we can see, a creator with higher relevant score will surely receive a higher reward. But this is not necessarily satisfying the group monotone, because we can see that what if the second ranked player increases her score from sigma 2 to sigma 2 prime, then the reward of the sigma 2 will increase by the amount of the red region in the middle. But however, the top ranked creator will suffer a loss indicated by the white region. And what does it mean? It means that if I am the top ranked content creator, and my field gets increasingly crowded in the sense that my competitors keeps improving their competence of their created content. And then the reward, even though I keep my the quality of my content, the platform should still decrease the reward to me. Yeah, this is also reasonable. So the good property of our proposed class of mechanism BRM says that we'll go through this very quickly. So the insight here is that under our proposed BRM, we can ensure that any improvement of each creator's utility will lead to an increase of the global potential function P. That means we can identify a global potential function P such that whenever each content creator selfishly increase her utility, this kind of increase is also reflected in a global function P. And this function P is called the potential function of the game. And more interestingly, we can identify such an instance of BRM such that such a global potential function P is exactly equal to our social welfare metric W. And when this global function P is equal to the social welfare W, it's when the platform choose the parameters in the rewarding mechanism F to be exactly the positional bias in the ranking result. So this what is the implications of this result? It says that when we pick a particular instance of the like the rewarding mechanism, uh, we can ensure that the potential function P will achieve at least the local maximum. If the our positional bias is known, then we can directly pick this rewarding mechanism to optimize the social welfare. However, if the R is usually unknown or noisy, or at least it's different across different users, right? In this sense, uh, a choice for the platform, of course, is to measure the R for different user, but it's not very efficient. What we propose is that even if the platform might not know the exact R, we can still optimize over the space of the whole BRM mechanism to guarantee social welfare that is empirically acceptable. So this is something like we are trying to optimize the function, but we don't know the exact the form of this function. So instead, we're trying to propose some surrogate a function and trying to optimize on this surrogate. We can gradually adjust the choice of our surrogate function to ensure that even if we don't know the exact form of W, by optimizing P, we can still get a good result in terms of W. So how this can be achieved? So we can formulate this problem in this kind of bilevel optimization. So here, M is the parameterized mechanism in our framework, which is the argument we want to optimize. And P is the induced global potential function of the game. And S is the equilibrium this game will eventually achieve whenever the platform proposes M. So you can see for each M, the platform chooses, it will induce an equilibrium S, and we want to maximize an objective function W of S. So actually, our empirical result shows that any zeros order optimization approaches would suffice to guarantee an empirically acceptable W. So we don't need to evaluate the exact gradient of W nor P, but instead we simply employ a very simple mechanism. We propose an arbitrary M at the beginning, and we ran for each fixed time period, we randomly perturb some element of M, and then we observe what is the new equilibrium, and we adjust then we decide whether we accept this perturbation or not based on whether the user welfare is increased by this perturbation or not. Yeah, such a simple mechanism would already guarantee us to find a very uh, good mechanism to optimize the welfare. So you can see here is the empirical performance of our proposed mechanism. So these baselines from our previous work, you can see we tried the exposure-based rewarding plan, engagement plan, and the OPT BRCM means that we're trying to find the optimal instance within this class using the zeros order optimization method. Uh, and BRCM star and BRCM1 means the theoretically optimal instance, given that we know the value of R, and an arbitrary instance within this class. And we can see that finding an element using the zeros order optimization would actually give us the highest empirical performance. And the right figure shows that the how this improvement in terms of the user welfare comes from. You can see that in the user utility distribution, user engagement distribution, I actually shifted towards the right side, like collectively. That means this mechanism actually induce a better resulting content distribution so that each creator in expectation will receive a higher utility. So yeah, this is our that second work. Yeah. And for our ongoing work, we're trying to deploy our proposed method in with researchers at Meta. So we are actively trying to find a solution in Instagram platform. When we talk about our solution, the the researchers from the real industry field, they pose two questions. Like the first one is like they believe our theoretical result is interesting, but they don't believe that creators in reality actually can figure out the best response or achieve no regret. Yeah, this is the critical challenge when we want to deploy it in the industry. And the second one is that they need some even simpler mechanism, but because they don't want the rewarding mechanism to be something like a black box, they need to use it as a guidance and release it to content creators. So it should be something very easy to follow. So if we want to find a real world solution, we need to keep these two in mind. So that's why we initiated the third work. So in this work, we relax our crucial assumption that the creators are actually smart enough to follow no regret learning or figure out their best response in the utility function. But what is the milder assumption we pose on the creator side? We actually allow them only assume them to they can do some local update. So you can imagine that allow assuming creators to figure out the best response means that at each round we assume each creator is smart enough to find the global maximizer of her utility function. But this is too good to be true. So what instead our assumption is like at each time step, each creator can at least make like tiny improvement in terms of their utility function. Yeah, they can choose an arbitrary direction to update the creation strategy. But as long as given other players the strategy fixed, the update of this my strategy would give me a tiny increase of the utility function. It would be good enough. So as a result, what affects our framework is that we cannot expect each content creator to achieve this Nash equilibrium of this game, but instead they can only achieve a local Nash equilibrium. So for those who are not familiar with these terms in a game theoretical framework, I can explain it as this. So the Nash equilibrium is like the global maximizer of a convex concave function. Um, but since we are relaxing our assumption on the creator's behavior, the profile of this function is no longer strictly concave. Yeah, it can have many local maximizers. But what we're actually assuming is that each creator will eventually achieve a local maximizer of this function. They might not be able to achieve the global maximizer forever. Yeah, but that is okay. Here is an example showing uh, uh, what is the outcome when we relax the creator's behavior. So here is an illustration showing that we have five user clusters, and each content creator can freely navigate in this landscape to figure out what is the group of users they want to cater to. So the left figure shows that a possible local Nash equilibrium creators might be able to achieve. You can see that some creators will eventually find the most suitable like user group they want to satisfy, and some creators will be stuck at the center of several user interest group and yeah, like the left bottom point. And the right figure shows that the optimal solution is that each creator will occupy exactly one group of users because this will give the maximum expected user engagement. So how can we design a mechanism to shift this outcome, a possible outcome from the left figure to the right? So and the key insight is that the platform needs to disseminate the knowledge about the user demand distribution to creators, because creators is not as informative as the platform. They might not know which group of user is underserved, which group of user is oversaturated, and they can only make some incremental updates in terms of their strategies. So it's very possible that they ended up being stuck at some local minimum. So a simple solution for the platform is that it can simply reweight the importance of different users. So we're still using this as an example. Uh, yeah, you can show this GIF. Sometimes the left user group is hard to discover because all creators lack the knowledge of the existence of such a group of users, and they will stuck at the middle. But if the platform decrease the weight of the center group of users, one creator can somehow cross this local attractor and to eventually find out the leftmost group of users. Yeah, so it's like the platform by reweighting the user groups, the platform is actually like reweighting the landscape of each creator's loss function. So it's such that when they optimize their own utility function, they can somehow escape the local minimum and to achieve a better local minimum or even the global minimum. So this is the insight behind our proposed solution. And we also have a theoretical justification saying that by reweighting the user in such a manner, what we can guarantee is that the new local Nash equilibrium achieved by the set of creators will strictly increase the user welfare. Yeah. Okay, so I leave the technical details uh, behind and simply um, jump to a conclusion. Yeah, the highlight is that we deployed our proposed simple mechanism in online A/B test and achieve a promising result. And we use the like-through rate as the welfare metric, and we performed a 3-week study. The symmetric A/B test means that we actually chooses 3% of creators and 3% of users independently from the platform and to match them exclusively compared to the base bucket, and we cluster the users into 10,000 groups by some demographic features and the level of activeness. And for each group of users, we assign them adaptive weight determined by our proposed solution. And overall, we observed an 1% increase of the like-through rate, and we also observe an increase of the content distribution from the creator's side, which is, by the way, a very promising result because the standard deviation of this like-through rate metric is like 0.2 percent. So 1% gain is like a five, at least 5 sigma away from the standard deviation. Okay, so to conclude this presentation, here are some takeaways. So the welfare optimization in online content ecosystem is hard due to the existence of content creators' selfish behaviors. But we are still possible to design some mechanism that leads to welfare improvement. Although a guarantee the global maximum is still challenging, but at least there is something we can do. And the human behavior modeling is double-edged sword in the sense that um, when we want to bridge the gap between the theoretical study and empirical implication, this is the key challenge we need to address because in order to derive some beautiful theoretical result, we need to make some assumptions about humans' behavior. But the human nature is volatile. There is no like unified theory to explain what the human choice would be. Well, so there are some future directions I want to propose. So we can incorporate some more additional effects. For example, the preference shift among users in this framework to make our framework more realistic. Because currently, we are assuming that user side preferences are still fixed. We are simply considering the dynamics of the content creator side, but in reality, actually both sides are undergo are shifting. And also, we're trying to understand how the generative AI industry would would influence the content creation industry. Yeah, because with the help of generative AI, the content creators could exhibit a totally different behavior. Yeah, this is also one of our ongoing project. Okay, so this is what I have to share in this presentation, and I'm happy to take any question.
Yeah, thank you so much for your presentation. That was super interesting. I think we can pause the recording now and then open the floor to